In this video, we will implement the method of lines that we described in the previous video. So, as a reminder, we will consider equations of the form partial tu equals lu, where L is a linear or nonlinear operator, a differential operator acting on u, and u is a function of t and x, time and space in this case. An example of such equations is an advection equation of this form, where c is the speed with which u is being advected. We described in the previous video the method of lines, where we can evaluate u of t and x on a set of grid points xi, and then u of t and xi is assigned a value ui of t, and the components, each component ui is part of a vector u of t, and so that allows us to write down this equation in vector form, where L now becomes a matrix operator. If L is a linear operator, then this operation is simply a dot product. So L is dotted onto the vector u, and we can write that in component notation in this form. So in particular for the advection equation, L would be minus c times the differential matrix Dij, which we know how to construct using collocation methods. Having done that, having discretized the equation in space, we just have to evolve forward in time, and the fundamental theory of calculus allows us to write this differential equation in integral form with a time step going from tn to tn plus 1. This formula is exact as far as time integration is concerned, and then we just have to approximate this time integral, and then we can use Runge-Kutta methods or Hermite type methods to calculate this integral and evolve in time. Any method that you can use for system of ordinary differential equations can be applied here. And in the last lecture, we discussed total variation diminishing Runge-Kutta methods, and we demonstrated that for linear equations this is equivalent to a Taylor expansion, so we can go from un to un plus 1 by multiplying with this matrix, which amounts to a Taylor expansion of the exponential of e to the L delta t. Another way to demonstrate this is to expand the function we're integrating here around Tn and then integrate it. If we do that, we get a formula that looks like this. So that's simply an integrated Taylor expansion. And then we can replace u dot from the equation of motion itself. U dot is equal to L times u. If this is a linear case, this is L dotted onto u. And then u double dot is obtained by differentiating this equation with respect to time, and then it's easy to see that u double dot, two time derivatives amount to L squared dotted onto u. So u dot is replaced by L times u, and then u double dot is replaced by L squared times u, and we can factor out u. So we have this expression right here. And then we can collect these terms together with this term utn, which we can bring to the right hand side, and then factor out everything. And then finally we arrive at this expression, which is the same expression we wrote down here, but we arrived at it in a slightly different way by doing a Taylor expansion of the integrand here. Okay, so with that in mind, let's go ahead and implement the method of lines. So first of all, we can do it using Mathematica as a, using black box, using ndsolve, which is a black box routine. So you can look up the documentation for how to use ndsolve. It's very extensive. There's also a very useful tutorial. If you go to Wolfram documentation and then search for method of lines and click on this tutorial, you will find a very thorough and useful tutorial that talks about the method of lines. So I highly recommend going through this tutorial, which explains why it's called the method of lines. It explains that basically a system of a PDE can be written as a system of ODEs, as we just discussed, and this tutorial actually does it for finite differences of second order. It writes down a set of 11 equations here, and then each of those is solved as a system using ndsolve, and you get 11 functions that are coupled through the differentiation matrix, and the solution is plotted here as a function of time and for each grid point, and you can see that for each grid point you get one solution or one line. So this is why this is called the method of lines. And there's a lot of very useful information here in this tutorial. I highly recommend going through it. And we will use a lot of these commands in what follows. Okay, so with that in mind, let's consider some Gaussian initial data. So let's consider a function f of x. That's the exponential of minus 16 x squared. Now, the issue with that function that you can run into is that if x becomes large, then you may run into underflow. So, and Mathematica will complain. So for that reason, I'm going to substitute this function with this. So if x is lower than 3, then I will allow this expression, but if x is higher than 3, then I'm just going to set this to 0, because the exponential of minus 3 squared, that's 10 to the minus 116. So that's a really, really small number, and if actually should probably write it like this. Okay, so I had a typo here. So e to the minus 16, 3 squared, we can write that as a number. It's 10 to the minus 63, so that's very small. So if x is lower than 3, I set that to 0 to avoid underflow, because, for example, if that goes to 10, you get errors like that. That's too small to represent as a normalized machine number. Precision may be lost. So that's why I'm using an if statement to protect myself from this. Okay. So this is a Gaussian. Essentially, we can plot it. So let's define some grid points. Let's define some interval. So let's suppose we go from A equals minus 7 up to B equals 13. And let's just plot it. Mathematica doesn't show us the whole range, so we can use plot range all. So now we see what our domain looks like. It's simply Gaussian with support near the origin x equals 0. Okay, so let's hide this, and then we can ask Mathematica to solve this advection equation. So let me write it down. So the advection equation looks like this. And then we need to specify initial conditions and boundary conditions. So the initial condition is u of 0, t equals 0, comma x is simply f of x. That's our initial data, this Gaussian. And then for boundary conditions, we're going to use u of t a. So at x equals a, that's the left boundary, we're going to set that to 0. And that should be sufficient actually. So that specifies that incoming waves here, they are stationary, u equals 0 on the left boundary. But because this Gaussian may reach the right boundary, u will not be 0 on the right boundary, so we're not going to set a boundary condition there for now. So that's the equation, the PDE, and that's the initial data, and that's the boundary condition. And now we specify that this is the variable we're solving for, it's u, and then x goes from a to b, and then t goes from t initial to t final, which we haven't specified yet. So let's do that. So let's say t initial is 0, and let's suppose that t final is 1.5. Okay, and then we really should specify the method. So for that, I'm going to use something from the tutorial I just described. So I'm going to use the method of lines, and for the spatial discretization, I'm going to specify we want a test product grid, and we want the method to be pseudospectral. So Mathematica will use a pseudospectral differentiation matrix. So let's execute this, and Mathematica very quickly obtain a solution. And then I can call this solution, let's call it solve. And then to set that solution as a function, let's call it usolve. And then I can type u/dot, that's a replacement rule. And then I want to pick up u from this expression. So I'm going to type solve, and then I'm going to type 1 to pick up the first element of this list. Okay, so now u is this function here, it is this interpolating function. So since u is a function, I can plot it as a function. So I can say plot usolve of, let's say, t final as a function of x, and x goes from a to b. And I should really say plot range all again. Okay, so that shows that the Gaussian has propagated to the right sometime tf later. And we can also create an animation. So to create an animation of this solution, I can use manipulate, and over here I can put the time t, and then use that as a parameter that I will vary from ti to tf. Okay, so now I can click on here and move that. So I see that as I move that, the Gaussian moves to the left. There are some artifacts here in the plot because of the grid points that Mathematica is using to discretize the problem spatially. But overall, it looks like a Gaussian propagating to the right. We can also plot the analytical solution. So to do that, the analytical solution is simply f of x minus t. So this is it. So again, these artifacts are actually because of the way Mathematica is plotting the solution. And we can plot the difference between these two, and that would be the error. So let's put u solve minus f here, and you see that the error is around 10 minus 2. So we only have 2 digits of accuracy. Basically, the third digit is inaccurate. Okay, so with that in mind, let's go ahead and implement the method of lines ourselves. There's always ways to improve the accuracy here. You can look at the Mathematica tutorial, but our purpose here is to learn the method of lines and implement it ourselves in a way that we can implement it not only in Mathematica but in any language. So let's go ahead and do that. Let's open another notebook and zoom in. Okay, so we want to solve a PDE. The first element we first need a differentiation matrix. So if you go back to the video that described finite differencing or pseudospectral differentiation or numerical differentiation, you can see that we can use this Mathematica command to construct the differentiation matrix of any order n. And in this case, I've chosen to use pseudospectral methods for differentiation. Okay, so again, I'm going to use the same initial data as before. And again, I'm going to use this if statement to avoid underflow. And I'm going to set this function to be listable because I'm going to need to apply it onto my grid. And again, I'm going to use the same interval as before. A is minus 7 up to b, which equals 13. So I'm choosing a b that's greater than a to give more space to the right for the Gaussian to move to the right. And then let's suppose that we use a number nx, that's the number of spatial grid points, that's 2 to the 10. That's 1024. And I'm gonna need the identity matrix. As we showed in the last video, the identity matrix shows up here. So let's construct that. And for convenience, I'm going to define nx minus 1 to be this number. Okay, and now, as we've shown before, for pseudospectral methods with Chebyshev nodes, we can define these angles that are equidistant, and then the grid points are given simply by this mapping from A to B of the cosine theta, where theta are these equidistant angles. Okay, so this sets up the spatial grid, as we've done this before when we did pseudospectral differentiation, and now we need to set up a time grid. So to do that, let's call the time step delta t, and we could set that equal to the special grid spacing, which would be b minus a over little n. So we could set that the time step equal to the special grid spacing. However, we may run into trouble. So let me delete this. Which we don't need. Okay, so we're going to run into trouble because we'll have a courant limit, which we will discuss later. But for now, let me first convert this to a number and multiply this by a small factor. And this will ensure that the time step is small enough so that the code is stable. You can always play around this number and try and increase it and see if you get instability, and we will describe how to do that and how to choose this factor here. Okay, so that's the time step that we've chosen, and then we can define this matrix D1 by calling this module here and passing the grid onto it and saying that we want the first derivative, and we call that matrix D1. And then we need a freezing boundary condition on the left boundary, and a way to do that, if you look at our equation, we want our left boundary to be frozen, where the incoming waves are coming into our domain from the left. So if u is frozen, that means partial t of u equals 0. From this equation, that means partial x of u equals 0 on the left boundary. So we can impose that partial x of u is 0 on the left boundary. In other words, if we inspect this, Lij uj is 0 if I equals 0 or 1, the first grid point. In other words, Dij uj must be 0 for the first grid point I. So to impose that, we can say I want D1 of 1, that's the first row of the matrix, and then all the points j to be 0. So all columns, first row. So the whole first row for all the columns is 0. Okay, we can do that for performance purposes. We can pack this array. We've shown before that this leads to a smaller memory footprint and higher performance. It uses some Intel primitives on Intel processors to make these operations faster. Okay, now let's specify that our operator L, as we just saw, is minus c, and c is 1, so it's minus c times d1. So our operator L is minus d1, and we will also need the square of that operator. So let's define L2 to be L dot L. We could also use matrix power. So we could use L2 equals matrix power, and then we could say L comma 2, and we would get the same result. But this would be a bit slower because this is only worth it for high powers of L, because it needs to compute the eigenvalues and eigenvectors of L to construct higher order powers. So for small integer powers, we can just dot L onto itself. And in fact, we're going to need even a few more powers. So L cubed is L dot L dot L, or I can just do L dot dotted onto L2, for example. And I'm also, actually I'm gonna stop there, I'm not gonna need L4. Okay, so we could implement the Runge-Kutta method in this way. So in each time step I could compute a vector u1 intermediate from this formula, another vector u2, and then plug those in here in this expression and compute the next step. We could do that, but in this case we can do things a little simpler. Because it's a linear equation, we can combine these steps into one, so we can construct this matrix and store it. And so let's do that for simplicity. Again, you can only do this for linear equations. In general, you would have to, if it's a non-linear equation that you're solving, then you should code it up exactly as you see it here. Literally, this is all you need to code up. Okay, so instead we're gonna code this up, which is a bit simpler. So basically, this matrix, let's call it M, is the unit matrix times what we see here, delta t times L plus 1/2 delta t square L squared plus 1 over 3 factorial delta t cubed L cubed. So we will build this matrix out of L. L depends on the differentiation matrix, and we're gonna call it M, and we're gonna store it in memory. And we're lucky in this case; it's a linear system, so this matrix doesn't change as you evolve. So we can just compute one and store it, and that saves time. In general, this matrix L may depend on you, and then you have to update it at each time step. And in that case, you might as well do this in 3 steps, because L will depend on you in general. Okay, and for performance purposes, after I construct M, I'm gonna pack it to a packed array. Okay, so let's pick a number of time steps. So let's pick 10,000 time steps. And then we build a grid in time. Let's call it capital T. And we can use table to build it. And then it's some integer it times the time step, delta t. And it, this time index, goes from 0 up to n, or nt minus 1. So we want to have nt time steps. Okay, so having done that, we need to set up a vector u that for our solution. And in fact, I'm gonna make that a matrix, so that will be a vector for each time step. So we know that u is a function of t and x. So I'm gonna represent that with 2 indices. The first index will represent time, and the second index will represent space. So first, let me declare that using constant array command. So that creates a matrix with size nt by nx, where nt is the number of time points and nx is the number of spatial points. And I set everything to 0. And then the first row of that matrix will simply be f of x. That's our initial data. So the first time point is going to be for index 1, and then all the special grid points, and we set that equal to f of x. So we can see what f of x is. So f of x is simply this function applied to each grid point, and we have specify the grid points x here. Okay, so we can do that, and then again for performance purposes I'm going to pack this array. It's not absolutely necessary, but if you're dealing with large matrices, you may run out of memory or your code may be slow, and it's highly recommended that you pack the arrays, and you can use byte count and you can use byte count to check the size of your array. So let me execute all of this. We're getting some output here. Let me suppress that. Okay, so let's try byte count u. That's quite large. Because I'm using a lot of grid points. If I didn't pack that array, I would have a larger memory footprint. And you can use developer packed array q to check if your matrices are packed. So in this case it returns true, which means u is packed. Okay, so having done that, let's plot our initial data. So that's u1, all that's the first time slice, the first time point. And we plot all of these as a function of x. So let's do that. So we see our Gaussian here as a function of x. Okay, so that was all preparation. Now our actual solver is very, very simple. So our actual solver is simply doing a matrix multiplication in each time step. Since we have built the vector u for each time slice, so in fact it's a matrix, we just need to do a matrix multiplication, a matrix vector multiplication at each time step. So let's do that, and actually let's also time it. So I'm going to use absolute timing. But before I do that, let's write the loop. So it's going to be do, and then it's really one line. So u of it plus 1, that's the next time point. All, so that takes all the special grid points, is m dotted onto u it all, and then it goes from 1 up to nt minus 1. And I believe this is it. Okay, so this was executed. Let me use absolute timing just to keep an eye on how long it takes to run this. Okay, so it took about 1 second to run this. Remember, we have a lot of time steps, 10,000 time steps. Okay, having done this, let's it means that the do loop has been completed. So let's look at how the solution looks like some time later. So to do that, I can use list plot. As always, I need to pair up each x with each u, and then I'm using transpose to do that. And then I'm plotting u at the final time nt for all values of x. And I'm using plot range all and join true to see the solution. If we didn't join the point, then we would get these dots as we discretized in space. Okay, and we can join them, and we see that the solution looks like a Gaussian sometime t later. So the pulse that was sitting here in the origin, x equals 0, has moved a little bit to the right. we can also, like before, we can compare this to the exact solution and look at the error. So to do that, we're subtracting the exact solution, which is f of x minus t. And here for t, I put, so x is a list of numbers, x, and I'm subtracting t, the last time point, which corresponds to nt. So we can use nt in here, or we can use -1. In any case, that's the last time point. So let's actually do that, nt. We could also use -1 here. So let's plot that, and we see that the solution is quite accurate. The error is around 10⁻⁹, and most of this error comes because of the integration method. That's Runge-Kutta of third order, which is relatively accurate, but not the best. The spatial differentiation is using a pseudo-spectral method, which is quite accurate, close to machine precision. So that's not the dominant source of error. So this spatial differentiation here comes through the matrix D1, which comes into L, which comes into M. It's already being factored into the M, this numerical operation. Okay, so having done that, we've talked before about how Runge-Kutta methods do not conserve energy. So let's look at the energy. Let's construct. First, we need the energy for the advection equation. To do that integration, we need an integration rule, and I'm going to use the Clenshaw-Curtis numerical integration that applies if we have these Chebyshev grid points. And if you don't know what the Clenshaw-Curtis rule is, you can go back to the numerical integration lecture. And over there we discussed how to construct the weights of Clenshaw-Curtis quadrature. Okay, so Clenshaw Okay, so this constructs the weights for our grid, and let's execute that. And then all I have to do is dot those weights onto my expression for the energy. Now, the expression for the energy is that, let me write it down here. I can use an inline formula or display formula here. So that's integral from A to B of partial x u integrated over x, that has to be squared. So normally this would look like this, and there would be a partial t here, and then there would be a 1/2. But from the advection equation we know that partial t u is equal to partial x u, so these terms are equal if the equation motion holds, and so we can, instead of having to estimate the time derivative, we're just estimating the special derivative, and we're setting c equal to 1, so we just need this. Okay, so let's do this numerically. So to do this numerically, well, first of all, let's check if this integration rule works before we use it. So to test if it works, we can dot it onto our Gaussian f of x. And let's see what we get. We get this number. We can also do integrate f of x from a to respect to x, from a to b. And Mathematica will do that analytically, actually. So we get the same result. And let's actually subtract them from each other. So we see that it's quite accurate. The error is close to machine precision. Okay, so we know we can trust this rule, the quadrature, the Curtis-Curtier, the Clenshaw-Curtis quadrature that we built here. Okay, so now let's calculate the energy. We have to do that at each time step. So I'm going to store the energy inside a vector. It's going to have nt components, and initially we set it to 0. And then I can use a do loop. So I can say do, and then energy. Going to have again an index it. And then, okay, so we need to integrate over partial x of u squared. So partial x of u squared, we're going to approximate that as d1 dotted onto u, the vector u. So to pick up the vector u, we're going to pick it up at time t, or that's the index it. And then we're going to take all the special grid points. So remember, if you do that, let's do it over here. If you do that, you're going to get a vector. That's a list of points. In this case, there's a lot to do. That's the Gaussian, essentially, that we built. And at some time later, the next time point is this, and so on. So we're picking up each of those lists or each of those vectors and representing u, the solution u, for each time point it. And then by dotting this onto this differentiation matrix, I'm calculating this derivative. And then I want to square that. So squared. And then this integral over dx is represented by this quadrature formula. So that numerical integration amounts to dotting the weights onto this integrand. So in this case, I'm going to take this function that I'm integrating and simply dot it onto w. And this is it really. I just need to say that it goes from 1 up to nt. That's the number of time points. That's 10,000. Okay, I'm going to do that, and then I'm just going to list plot the energy. Okay, so the energy looks roughly constant, but this is not really very informative because I want to know what happens at a closer scale. So I can subtract the first element. I don't know what the energy is, but I know what the initial energy is. So I can just subtract the initial energy at the first time point. And that will let me zoom in a little bit. And now I see what's going on. So we see that the energy is not being exactly conserved. The error is small, so we didn't see it when we plotted earlier, but it increases linearly with time. So that means as time goes by, really the energy error is going to accumulate and start to play a role. So already here I'm losing 1 digit of accuracy, and if I go for longer, I'm going to lose more accuracy. So you may lose 6 digits, 5th, 4th, and so on. As time goes by, this is going to get worse, and it may start impacting the qualitative nature of your solution. But this is all to be expected because we're using a Runge-Kutta method, which is not time symmetric, and so it doesn't respect symmetries of the underlying continuum system that we're solving. That's not the only issue with the Runge-Kutta method. Another major issue is the stability. So as you see, I had to use a very, very small time step here. So it's 100 times smaller than the special time step. The reason I had to do that, it has to do with the Courant limit. Or you can look up the Courant Friedrich-Lewis condition. So you can Google CFL limit and look it up on Wikipedia, and you can get an estimate for the advection equation and so on of how to compute it. But there is a easier way in our case to estimate what the limit is, and that's because we're using a linear equation like that, where u is updated by m dotted onto u. We know from linear algebra that such an iteration will be stable if and only if the eigenvalues of m are absolutely smaller than 1, smaller or equal to 1. So I can simply compute the eigenvalues here. So let's say eigenvalues m, and then I'm gonna compute the absolute value for those eigenvalues, and then I'm gonna pick up the maximum just to look at, we just need the maximum to see if we have stability. So let's put that line here and see the output. So here we see that the maximum eigenvalue is 1. That means we're stable. If you do this calculation and the maximum eigenvalue, its absolute value, is larger than 1, then that means the iteration will be unstable. That eigenvalue will start to dominate as you iterate, and your code is gonna, your value of u will explode exponentially, and your error will explode exponentially. So let's try to see if we increase time step here. Let's try and increase it to 0.1 times the special. And this is not really the special grid spacing, because that's not constant, but it is the average grid spacing. Again, the grid is not equidistant. If it was equidistant, this would be the grid spacing. So instead, you can view this as the average grid spacing. So let's use a bigger factor here, 0.1, see what happens. Okay, we get a huge factor here. That's 1,000. So if I try to do this iteration, Mathematica will crash. So let me save this just in case it crashes. Okay, so let's try and execute this. And as you see, we've gone over to a lot more than 1 second. And basically, Mathematica is computing things that are not a number, and it's just very slow. And you're gonna have to wait a long time to see what the error is. So I'm not gonna wait. Instead, I'm just gonna have to abort. If it doesn't run in a second like it did before, you know something's gone wrong. So I'm gonna abort this evaluation. So that's evidence of instability. Let's try and use something smaller here. Still, the eigenvalue is larger than 1. Let's try something smaller. Still larger than 1. Let's try 1.5. Still barely larger than 1, so still unstable. Let me try and run it with this. Okay, still not running, still the code is crashing essentially. Let's try 11. Okay, so that's 1. I'm trying to get as close, but just make it barely unstable. 12. 13 maybe. That's still stable, borderline. Okay, so this is barely unstable. We can try and get closer. Okay, that's very close to unstable. So it's barely unstable. Let's see if that runs. It may run for a bit. So it did run. So here we may not see the instability right away because it develops very slowly because the eigenvalue is very close to 1. So that's why this didn't crash. Although it's barely unstable. So you're gonna see the instability later in time. You don't see it right away. So sure enough, it ran, but there's instability here. We see an explosion here. Some numbers of order 10 to the 17. So you can see that this is indeed unstable. And there's no point to plotting the error. It's going to be huge. Okay, so we pick a smaller number than that to ensure that the eigenvalue is 1 or lower, the maximum eigenvalue, and then if we run this, then the solution looks okay. No instability. Okay, so that timestamp is really small. It's 100 times smaller in this case than the average special step. If we use finite difference methods, that could be a little bigger. The reason delta t is so small is that these points are finely spaced near the edges A and B. So the current limit depends on the finest grid spacing, not the largest grid spacing. So because we're using pseudo-spectral methods, that makes time step more restricted because delta x is more restricted near the edges A and B. So for finite differences, the grid spacing would be constant everywhere, and you could use a larger factor here, up to 1. But in any case, there is a limit here. So the Runge-Kutta methods are conditionally stable. They are subject to this Courant limit, and they don't conserve energy. Okay, so as we've discussed when we talk about ordinary differential equations, we can remedy these issues by using these methods that are time symmetric. So we can use the trapezoidal rule as described here, or we can use a Hermite rule as described here in the last lecture, and so on. So we can also construct higher order rules. So let's implement that. So to do that, all I have to do is change the matrix M. Everything else is ready, essentially. All I have to do is change this matrix. So let's do that. So we want to build this matrix here. So I'm going to comment this out. And instead I'm going to define M to be, so let's see, I'm still going to need a quantity that looks like that. So we have a unit matrix here, and delta t times L plus the delta squared over 12. So I'm going to put a 12 here. And I don't really need this. And then I need the same expression here, but with a minus here. So I'm going to need this with a minus, and that's the inverse matrix. So we can compute that simply by saying inverse. And then these two matrices are dotted into each other, so I can use dot to calculate this dot product. And this is it. So that's the only change we need in the code. everything else should stay the same. So I switched from a third order Runikuta or RK3 we switched to a Hermite rule. Which is, we know, is fourth order accurate when we looked at the harmonic oscillator, for example. If we wanted, for example, to do the trapezoidal rule, all I have to do is skip this term and skip this term, and then that would be trapezoidal rule. So let's execute that and see what happens. Okay, so that's a good sign. The eigenvalue is not larger than 1. And let's run it. As you can see, it took 1 second. Again, it didn't take more time. Although this is an implicit method, because I inverted this matrix in advance and stored it, it's simple matrix multiplication. That's all we're doing in each time step. We're doing this multiplication. So the cost is the same for the implicit and the explicit method. The cost is the same. But that's the case only because we were solving a linear system. So we were able to solve this equation and store this matrix M. Otherwise, we would have to do this iteration. At each time step, we would iterate an equation that looks like this. In that case, it would take more time to do the implicit method compared to the explicit method. But for linear system, you should surely use an implicit method. It doesn't cost any more. So let's look at the solution. Okay, the solution looks like it has propagated, and let's actually check. Let me execute it again, make sure. So we're starting from u being 0, then initial data, then we do this, and then we plot the solution. And then let's plot the error. There's something wrong here. It looks like u is propagating further than it should. So there might be some typo here somewhere. Okay, there is indeed a typo. We're missing the 1/2 here, which this should like the trapezoidal rule, but it doesn't. Okay, so that should be corrected. So let's run it. Okay, so now this propagates the right amount of distance, and let's look at the error. So now the error is 10 minus 13. If you remember earlier, it was around 10 minus 8. So already the error looks much lower for two reasons. First, this is a fourth order method, which is higher order than a third order method, but also it's a time symmetric method, so it's more accurate and conserves energy. To show the conservation of energy, we can compute the weights. Again, we don't have to, they're the same as before. And let's look at the energy conservation now. Okay, so we're getting something much better. So instead of 10 minus 9, we get something that's 10 minus 12. And instead of linear growth, we see some oscillatory behavior. And this is really not due to the non-energy conservation of the method, but it's due to the way we're calculating this integral. We may lose some accuracy, and also as the pulse moves to the right, some of the tail of the Gaussian starts escaping, and so that's the reason we may not be conserving the energy exactly to machine precision. If we extend the domain more to the right, so if B becomes larger, then the tail will not escape from the right, and then this will be even more accurate. But anyway, we already see that we don't have this linear growth anymore, and energy is conserved. The other point that's important is the stability, so the Courant limit. So as you remember before, we couldn't take very large time steps. Let's look at what happens now with this implicit method. Let's look at delta t here. Let's try and double it and see what happens. You see that the eigenvalue is still 1, the maximum eigenvalue. Before it became very large. Let's try and make it, you know what, let's do it 10 times larger. The eigenvalue is still 1. And in fact, I can try and run this. It didn't crash. And okay, the problem here is that the Gaussian reaches the right boundary and gets reflected back and forth. So we get some numerical noise here, or it may actually escape. But anyway, let's try and evolve for less time. So let's try 5,000 time points, and let's see, now that runs in half the time, of course, and you see that the Gaussian hasn't escaped yet, it's still in here. The error is relatively low, and the energy is still quite accurate, 12 digits. So remember, we couldn't do that before with the Runge-Kutta method. We couldn't take such large time steps. Again, this is 10 times larger than before. So we were able to evolve for much longer in half the time. So essentially we get a factor of 10 faster performance, or you can trade that for higher accuracy. And you can actually make that even smaller or even larger, so we can even try 1. So that's 100 times larger than before, and the eigenvalue is still 1. And now I know I have to reduce that to 500, and now the code ran in only 0.05 seconds, and it propagated to the same point, so the final time is the same, but we got there much faster. And now the error is probably larger. So the error is larger because delta t is 100 times larger than before. And the energy conservation, let's look at it, is still 10 to the minus 13. And that's very impressive. So although the accuracy of the solution is only 5 digits, the accuracy of energy conservation is still close to machine precision. So essentially now energy is exactly conserved because our formula is time symmetric, and we're not restricted by delta t, so you can take as large a delta t as you want. The eigenvalue is still going to be 1, so that method is unconditionally stable. The same is true for the trapezoidal rule or the lock-in rule. These time symmetric methods are unconditionally stable. That means you can take arbitrarily large delta t. Of course, it doesn't mean that you should take a very large delta t, because as you see, you start to lose accuracy here. But you lose accuracy because of truncation error. So we were truncating this series. The 2-point Taylor expansion is truncated to 4th order. So you're going to have an error term, which is relatively small, but it's still there. So it's a term that's of order delta t to the 4th for the Hermite rule. If I want more accuracy, I can simply decrease delta t to something smaller. As you saw, I made it 100 times larger. I get 100 times better performance compared to Runge-Kutta. So you can either make that delta t a bit smaller. As you saw, if you settle for 0.1, that was enough. to get something very close to machine precision, or we can use higher order rule. So this is a fourth order rule. Let's try something slightly better. So let's change that to 10. Let's change that to 10. And then we're gonna need the term delta t cubed, 120, and we need L3 here. And we need the same term here, but I think it's with a minus. If you watch the numerical integration video, you may remember that this is the Lockheed rule. So let's comment that out. And again, this formula is time symmetric. Is the Hermite rule extended to the next order, so it's a 6th order accurate rule, although we're using only terms up to delta t cubed here and delta t cubed here. So let's run this. Again, it doesn't cost anything more to run. It's still running 0.5 or 0.6 seconds. It will get to the same point, but let's look at the accuracy now. Instead of 5 digits, let's see, we have 8 digits of accuracy. And the energy is conserved in the same or slightly better, to close to machine precision. As a final comment, I want to say that we use pseudospectral methods here. If you wanted to switch to finite difference method, you can simply replace this pseudospectral here. You can simply replace it, let's say, with fourth, or with a fourth order finite difference method. All you have to do is put 4 here, and then we're doing finite differencing. But at the same time, you have to swap out these commands for something different. So you would have to use, let's see, let's comment this out. So you can say x equals table A plus I times the grid spacing, which is basically this B minus A over n, and will go from 0 to n. And this is it really. That's the only change. We just changed the grid to be an equidistant grid, and we just change the differentiation matrix, which is built automatically by Mathematica with this command, or you can build it by hand using the Lagrange interpolation formulas and differentiating them. So I see that I've copied, pasted something twice here. So let me delete that. Okay, so instead of the pseudospectral matrix, I have the fourth order matrix here. And I better comment out x. And let's convert this to a number. And let's run it. See a potential issue here. Is that the eigenvalue is slightly larger than 1. So we may run into instability. Okay, this looks stable. The accuracy is much lower, of course, because we're using finite differences. So to improve accuracy, you can use more special grid points. So right now we're using 1,000 grid points. We can use more or we can increase the order of the method, so we can try a 6th order finite difference scheme. Again, there's a worrisome issue here that the eigenvalues look higher than 1. This indeed causes instability here. One issue here is that these derivatives may not be computed very accurately if you're using finite differences. So I recommend that you always check the eigenvalue of your matrices and see if they are greater than 1 or not, to make sure you're not running into instability problems. So let's try a smaller time step. Okay, looks a bit better, but still probably not stable. Let's try a Hermite rule. So that would be 4th order finite differencing with a 4th order time integration method. Okay, that looks closer to 1. So this seems to run okay. We may still run into instability if we evolve for longer. And let's look at the error. So the error is acceptable for a 4th order method, but still not great. So of course, it's highly recommended that you use pseudo-spectral methods if you can, if your problems are smooth. Otherwise, if you have to use finite difference methods, I recommend you use many more special grid points. Let's try an even smaller number here. Now it should be stable, although it's still slightly higher than 1, so there still may be instability later. Because I use a much smaller delta t, it doesn't propagate very much. I would have to use more time points to let it propagate for longer, and of course that will take more time. And then you can check the error here. It's the same as before, so it didn't improve much. So although I decreased delta t, it didn't get more accurate, and the reason is that we're dominated by special error. So because I didn't improve delta x, the accuracy did not improve. So right now the only way to improve accuracy is to either increase the order of the method or increase the number of special grid points. Finally, as a final reminder, I think we are aware of the benefits of implicit methods now. For non-linear equations, it may be more convenient to use Runge-Kutta because they are explicit methods and easy to code, and we would just have to code these 3 steps at each time step. Whereas for implicit methods, we would have to code up something like this, and we would have to iterate at each time step until un+1 converges to a fixed point value. So that would be a fixed point iteration. So you do many more steps in each time step, many more iterations. So that would have more cost. But again, remember, if you're solving a linear system of PDEs, then it's highly beneficial to use these time symmetric methods because you can solve this iteration analytically and then invert this matrix to store it. And then the performance of your implicit method is the same as the explicit method. And that concludes this video. Thank you for watching.